lesson 1.5, analyzing limits of trig functions. So their comment there is most of the work we've done so far has been with polynomials or rational functions. Okay, so trig functions, there's some different methods we can use. Okay, one of which you'll notice what we're talking about right here, direct substitution. Okay, that is still an option. Okay, plug it in and see what happens. So let's try it on A. The limit as theta approaches pi over 3 of cosine of 2 theta over theta. If we're just plugging it in, remember when you plug it in, you can drop off the word limit. So the cosine of 2 times pi over 3 divided by pi over 3. Well, what is 2 times pi over 3? 2 pi over 3. So we're going to have the cosine of 2 pi over 3 divided by pi over 3. Now, what's the key that you have to figure out here?
Cosine of 2 pi over 3.
Yeah. So, with that in mind, I would ask, what's cosine of pi over 3? So I know Logan's a triangle person.
Yeah.
Is that kind of what Eli is?
B1 half. Yeah.
I can't draw my triangle near as quick as Logan can because my brain doesn't normally do this. So if we're doing cosine, so I would start off thinking about cosine of pi over 3 or cosine of 60, which is going to be the opposite over or did I do that wrong? I did something wrong. Oh yeah, okay.
It's just cosine.
Cosine, yeah, sine.
You said opposite.
I did. So it's adjacent over hypotenuse, right? So toa. So adjacent over hypotenuse, which is 1/2. Now, 2 pi over 3. Where is 2 pi over 3? Because pi over 3 is right here. Where's 2 pi over 3? 2 pi over 3 is right here. So what do we know about the second quadrant? Cosine is negative because all students take calculus. Are we there?
Yep.
So then we end up with negative 1/2 divided by pi over 3. How do we divide fractions?
Keep change flip.
Keep change flip. So negative 1/2 times 3 over pi, which is,
Negative 3 over 2 pi.
I would just leave your answer like that. Okay? So direct substitution works there. And in all honesty, you have to go past the cosine of 2 pi over 3 part, but these other answers are equivalent as well, just not nice form. Okay, B. Have you looked at B? Limit as theta approaches pi over 2 of 3 sine squared theta. So,
3 sine times pi over 2.
So right. Realize it's 3 times the sine of pi over 2, and you're going to square the result of the sine of pi over 2.
So pi over 2 would be 1. Then you square that, still 1.
Pi over 2 being the same as 90 degrees, right? That ordered pair is 0, 1. In an ordered pair, it's cosine sine. So, yep. 3 times 1 squared, or in other words, 3. Okay? Easy enough. Now, just like some polynomial functions where a function value is not defined, yet a limit will exist, the same will occur with trig functions.
Because if you plug it 1 over 2, then it's going to be 1 minus 1.
Okay, so if we plug this in, the sine of pi over 2 minus 1 over the cosine of pi over 2 quantity squared. Well, yeah, sine of pi over 2 we just did, right? So 1 minus 1, which is 0 on top. What's the cosine of pi over 2?
And also be 0 because the x value is 0.
Yeah, 0. So we end up with 0 over 0. This is, remember, I refer to this as our indeterminate form. And so this is, we're stopping. We're not going any farther with this one, but this is the idea that substitution still doesn't always work. Okay, when you hit this indeterminate form, it doesn't mean you're done. It doesn't mean it doesn't exist. It means something else has to be done. We have to go for a different technique. Okay? Okay. Now, if you algebraically determine that a function is undefined at a value, does that mean the limit does not exist? Can you look at the graph? How do you analyze the limit when no calculator or graph is permitted? We need to use some trig identities and rewrite the function. And they suggest that here. So, now, well, they don't have a limit there. They just have a graph, don't they? So let's look at this equation, or this expression. Sine x minus 1 over cosine x quantity squared. Okay. Oh, I do have a limit down here. It's just not written in there. So before we'll readjust. Oh. Basically, okay. I forgot. This is a continuation of the problem that we just did on the back side that came up with that indeterminate form, yes? So we're going to look at the indeterminate form and try and see what we can come up with. Okay. They suggested trig identities and rewrite. You guys both had me for pre-calc, so your brain needs to think purple paper. Mm-hmm. Okay? All that fun stuff on the purple paper is technically fair game, just without a purple paper in front of you. Now, there are some identities on that page we use more than others, and those are the ones that usually come into play. Okay? So, that denominator, cosine x quantity squared, that's the same as saying cosine squared, right? Mm-hmm. What do you know about a connection?
Sine squared minus 1.
Because you're thinking of a Pythagorean identity?
I thought it was sine squared though.
So, I didn't catch which way he said it, so there is squared in there. He didn't say squared, but.
No, I'm saying I thought it was sine squared.
It is.
Isn't that what it says? Sine squared minus 1.
I'm just trying to figure out how it's going to relate to this.
Okay. Give it a chance. Give me a moment and it will relate. Okay. So Pythagorean identity reminder, cosine squared plus sine squared. I just said that totally backwards of what I wrote, but it's 1. Now, so what you have to realize is there's a connection between cosine and sine here. Let's replace the cosine squared. So still sine x minus 1 on top. Cosine squared can be rewritten as, what did Eli say? 1 minus sine squared.
Okay, so I said sine squared minus 1.
Okay, did you? Yeah.
That's not the same.
But you were headed there.
Yeah.
First Pythagorean identity practice of the year. I give you credit. You knew you had it. You just had to figure out the details. Okay. We're allowed to be rusty. Does anyone see what I can do with that denominator? Factor. Okay. So my numerator, I'm still going to leave it as sine x minus 1 here in a moment. Actually, I may rewrite that, but this factors into 2 parentheses. This is the difference of squares. Square root of 1, so 1 breaks into 1 times 1. Sine squared breaks into sine x times sine x, yes?
Mhm.
And since it's the difference of squares, we need a plus and a minus. We're not quite there yet, but are we closer? We are. Okay. We are off by a sign. And when I say a sign, I mean a positive negative sign, not a sine x. So I'm going to, I guess I'm going to continue on the other line here. I'm going to flip that around. So I guess think of it this way. If I flip that around, it's -1 plus sine x. Take the negative and factor it out. And you guys can do some of this in your heads. I'm writing down a lot. But if I take the negative and I factor it out, I'm left with what? +1 minus sine x over what I already had, which was 1 plus sine x times 1 minus sine x. And did we get to a point of canceling? Yes. And I wrote out a bazillion steps. You could have definitely shortcutted some of those steps out.
I feel like it might be necessary.
-1 over 1.
So -1 over 1 plus sine x. So all that work, we just showed that this is equivalent to this, yes? Now, huh?
Sometimes I forget you can just factor out signs.
Yeah, you can.
Take the
So now,
sign.
the limit we had on the previous, at the bottom of the previous page, was the limit as theta approaches pi over 2. So I'm just going to use x here. And it was of this, the sine x minus 1 over cosine squared. This is equal. So now I can plug in and use the -1 over 1 plus sine x to do my limit. And we're doing the same limit on the front page, or on the previous page, where right here it was indeterminate. By working with Pythagorean identities, we're going to be able to make this doable. Because now what are we going to do? -1 over 1 plus sine of pi over 2. What was the sine of pi over 2? Sine of pi over 2 from the previous page was 1. So you end up with -1/2.
Oh.
Okay. And here's the deal, guys. You know, they put a graph here, but, you know, the question was, you know, can you look at the graph? How do you analyze? Well, this was as x approaches pi over 2. 3.14 divided by 2 is like 1.5, so it'd be about right here in the middle. Could you tell that was going to -1/2? I can't. Now, if I have a graphing calculator in front of me and can manipulate it, sure, but to just look at a picture of a graph? No. Okay, so if you guys want me to, later, I can dig out copies of that purple paper. It'd be helpful to have one on hand. You can't use it on tests or anything, but, you know, I don't think, you know, like Pythagorean identity, you guys are going to remember that. You guys, well, you already knew it. It was just how to use it. So, okay, moving on.
I haven't memorized this here.
What? Oh,
Having the identities memorized this here instead of relying on the paper.
yep. Okay. Use your new skills to evaluate each limit below by first rewriting the function and using identities. I may need to dig out the purple paper sooner than later, but I think we'll try this.
Cotangent is cosine of time. That's about the only thing I remember.
But that's what you need to remember.
Yeah.
Okay, so if you plug it in right now, I'm guessing it's not going to work because of how they have it written. Okay, so if we work to adjust this, Still writing the limit as long as this is the limit, so I don't forget. The limit of theta as theta approaches pi over 2. This is 2 times cosine theta times cotangent, which cotangent is cosine over sine.
Basically just to use cosine squared for sine.
Okay. Which, I mean, it would have been nice if it canceled out, but it doesn't. But if nothing else, it's going to make it a lot easier to work with here. So about the only thing I can do here is to clean it up a little bit. So this is 2 cosine squared theta over sine theta. And let's try and plug in the pi over 2 and see what happens. So 2 times cosine of pi over 2 squared over sine of pi over 2. Yeah, it does.
Cosine of pi over 2 is 0.
Okay. What's sine of pi over 2?
1.
So you just end up with 0 over 1, which is 0. It's not in indeterminate form, it's 0. Okay. Now, in that scenario, could you have done it with cotangent? It's just that cotangent isn't, I don't know, with pi over 2, we use sine and cosine and adjust from there. So it would be, you know, to me, that one was an easier one that way.
Is this one going to be sine times cosine over sine over cosine?
Mm-hmm. But we can clean it up pretty quickly.
Just keep change flip.
Yep. So right now I have sine, cosine.
So you're basically just multiplying by cotangent.
Yeah.
You could think that too. Okay. So when you keep change flip that, what goes up top?
Cosine.
It's the cosine, yes. So you end up with sine theta, cosine theta times cosine theta over sine theta, right? That's one way to look at it, I guess. Anything cancel this time?
The sines do.
Sines do. And then you're just at cosine squared. Okay. So even if you could have done it on the, I'm not going to say you couldn't have done it on the original, but actually, yeah, it's not that we couldn't have done it, it's just going to be easier this way. So cosine of pi over 4 quantity squared. What's the cosine of pi over 4?
It's going to be 1 over square root of 2.
Which I like to use as, well, that might actually be better in this case, wouldn't it?
Because you're just squaring it. So
Yeah.
It's going to just be 1/2.
I was going to say square root of 2 over 2 squared. I'll be honest, if you use 1 over square root of 2 in this scenario, it's actually going to be easier because you're not going to have to reduce. But just remember sine and cosine of pi over 4 are both square root of 2 over 2. So this becomes 2/4, and I have to reduce mine to 1/2, whereas Logan would have just been at 1/2 from squaring. So normal rule of thumb, I would use square root of 2 over 2. Okay, see? We haven't even dug out the purple paper and we're making progress. Sine cosecant over 3 theta. What do you know?
Oh, the sine and cosecant will cancel out because cosecant is just 1 over sine.
Yeah. So if I just rewrite cosecant as 1 over sine theta. Well, what's sine theta times 1 over sine theta? Yeah, they're going to cancel, right? So we end up with the limit as theta approaches pi of 1 over 3 theta. And this math just became incredibly easy because we have
1 over 3.
1 over 3 pi. There's no trig to do there. You're just plugging it in.
Yeah, I like those problems. Those are nice.
Okay. Okay, have you discovered a pattern in all of this yet? If you always try direct substitution first, 3 things will occur. Okay. You could get an answer, which, in other words, in the form of a number value is what I'm going to write. You could get a number, just a good old everyday number. That's an answer. Okay. I'm trying to think if have we seen this today? You could get a number over 0. Okay. And a number over 0 is one of those where you're not necessarily done. It doesn't just automatically mean undefined.
I mean, we got 0 over 0 at one point.
Well, 0 over 0 is going here. That's a different scenario. Okay. So, with the number over 0, I have things written down that you can think of, such as factor, cancel.
But if you try one of those and it doesn't work, does that mean it's D&E?
Usually something works. Factor, cancel, rationalize.
Are we going to have to try all of those, or is it just going to be like...
No, usually you have an idea. Because, I mean, if it can factor, that will probably take care of it. If you need to rationalize, that will probably take care of it. Okay.
0 over 0 over indeterminate.
I would say this one is indeterminate form. With indeterminate form, you're inspecting one-side limits. You know, you're looking at things like infinity, negative infinity, D&E, you know, really almost in a way you're doing some of these same things. You're looking for, you know, what can I do? Okay, keep going. Don't give up.
10 pages per minute.
That math is not mathing for me.
Oh.
He said 10 pages per minute. I think he meant 10 minutes for a page. Okay. Now, okay, later, much later, like it's like Unit 3, we will learn what is called L'Hopital's rule. Looks like L'Hospital's rule, but it's pronounced L'Hopital's rule. We need derivatives to do that, but it is a way to deal with limits in the indeterminate form. And it's really probably the easiest way to deal with the indeterminate form. We just don't know derivatives yet, so it doesn't help us. Okay? But that's why we're looking at other methods, in case L'Hopital's rule isn't an option. So from now, we talked about these briefly the other day when you guys were reviewing for quiz. These are 2 special limits that, as calc students, it's just good to know. Okay, so these are just things I'm going to say memorize. Okay, we talked about this one the other day. The limit as theta approaches 0, if sine of theta over theta equals 1. We're going to do a little bit of work along here with that. The other one we have is the limit as theta approaches 0, still 0, but it's 1 minus cosine theta over theta, and it's equal to 0. So your numerators and your answers are what change there. Sine theta equals 1, 1 minus cosine theta equals 0. And I would probably say the sine one is the one you probably are going to use more. But if you can recognize these, it's going to help. They can make certain problems easier. Okay? Now, what does it suggest? Use a graphing calculator and the table feature to evaluate the following trig limits. Can I just tell you the values?
I trust you.
I'm just thinking that, you know, time and I don't know. I'm just going to go with I'll tell you the values if you don't mind. Let's look at the first one. The limit as theta approaches 0 of sine of 2 theta over theta. Now I'm going to fill in these boxes. And I have them each to 3 decimal places, it appears. 1.998, 1.999, D and E does not exist, 1.999, 1.998. What do you think here? The limit as theta approaches 0 of sine of 2 theta over theta.
Maybe 2. Yeah. Which kind of makes sense because on the equation, really just 2 theta instead of theta, the special limit thing.
Right? The normal rule is 1, but you put a 2 here. The point is it becomes a 2. Are we? And that's the connection we're trying to make here.
Can I make a prediction that this next one is going to be -3, potentially?
You can predict all you want. Okay, you ready for my values?
Yep.
I have 0.446. 0.044. D and E, shocker there, right? -0.044 and -0.446. So,
What, 0?
it does not actually.
0.04.
0.0.
004.
Well, notice, what do you have going on difference from left and right? One's a positive, one's a negative. Now, you could maybe, I feel like you'd have to do a little bit more work. You could maybe try and see if it goes, you know, like argue, well, it looks like it might be going to 0. But it doesn't on this one. Now, I know, so Logan's prediction was 3 or -3, whichever it was. Why not?
Because it's cosine -1, not 1 minus cosine.
Yeah.
No, that's why I said -3 instead.
Yeah.
Okay, I see. So,
Or wait, no, it equals 0. Oh, I thought it equaled 1.
well, and that's the other thing. Notice, it's not that one at all, is it? Okay. Because, yeah, if you're multiplying by 0, it doesn't work. So that's just right there to go to show that you reverse the order, that one doesn't work.
Maybe this one is 3/4. Or 0.75.
Well, you want my values to figure it out?
Sure.
0.738. 0.749. Take a guess.
D and E.
D and E. 0.749. 0.738.
Bang.
So, you're seeing something that works here, right? Okay. Yes, you see the sine theta over theta. You see the 3/4 there. So yes, 3/4 or 0.750. Okay. What?
Or it could be
Is it going to be 0.5 or or a range?
Yeah, okay.
Yeah.
-0.223. -0.022. D and E. +0.022. positive 0.223.
Danny again.
I'm gonna say 0.
Well, that was my initial thought.
Because
Last time
one
we said
minus
that.
this time.
So- And it is the 1 minus this time. I have to go back and, for some reason, I have D&E marked out, and then I do have 0. And, okay, guys, it comes down to,
Comes down to because it said so.
Yeah.
No.
Yeah, rules.
first of all, important to notice that, yes, it is the same format, right? That 1 minus theta, cosine theta over theta. The other piece is, and I have written in here, the direction to go would be to analyze each side. Okay, if you analyze each side, or if you were to look at the graph, you would see this one does come out to be 0. Notice the difference in the original format of the problem.
1 minus versus.
Okay. So, and I mean, part of what I'm saying here is, yes, those look like they're approaching 0, but they don't actually. This one, well, now we want to say, oh, well, maybe they aren't, but they do actually in this case. Excuse me. Okay. And if we wanted to go into a bunch of extra work about proving it, we could. But I'm guessing you guys don't.
Well, tell me that.
True.
We're ready.
People smart.
Well, but this was the big page. Okay. Moving on. 9. Some algebraic tricks with properties. Okay, well. Do you have guesses?
Well, I feel like this one could just be. No, not really. Can you reduce the thetas?
So 7.5.
I don't want to reduce thetas because that's part of the setup for our special form, right? But, I mean, here's what you can think of. This 3 is just a whole number, yes?
Yeah.
One of the things you can do with that 3, that whole number, is you can bring that out front. So times then the limit as theta approaches 0 of sine of 5 theta over 2 theta. So then what are we looking at?
5 halves is just pi over 2.
3 times 5 halves, which is the 15 halves.
Why? Because you make sine theta 1?
Well, okay. So go back to example C right here. As theta approaches 0, right? It was basically, I mean, we can go to prove it, but the shortcut is that you can just grab the 3 and the 4. The difference is on the one we're working on is that there is that value of 3 out front, so multiply it by 3. Now, I mean, there's another way I can show it, but to me, that's the easier way to see it. Are we okay with that way then? Okay. B.
I have a guess.
You have a what?
I have a guess.
What's your guess?
That's right. So I'm thinking 1 minus cosine is 0 plus sine over 3 is 3.
Well, you
over
can divide the
1
fractions up. Yeah.
Yeah. So officially, yeah, you guys are both on the right track. We can split this into 2 fractions.
Because then it'll make that first part 0.
Because then you can say 1 minus cosine theta over theta is one limit, plus the other limit, which is sine of 3 theta over theta. This one we know is 0.
No,
This one,
it's going to be 3.
yeah, basically it's 3 times 1, or in other words, 3.
So I just combined steps.
Yep, you did. I mean, yeah, you guys both said valid things. You just, you know.
You did it the proper way.
Yeah, the proper way to separate the fraction.
Okay,
Oh, fun.
back page. Okay,
Dude,
Talks
we hardly
about-
talked about the squeeze.
we have, which is why I don't know how much of this page I actually want to do. I was debating, to be honest.
We could find the limit on the bottom.
Okay, evaluate the limit using the squeeze theorem.
Okay.
A talks about explain why you cannot use the product limit law. In other words, why can we not just break this into two limits here and say the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x. But the problem you run into there is this sine of 1 over x limit does not exist. And so then it just becomes messy. Okay? Just becomes messy trying to figure that out. Now, what this suggests is they consider, on part B, consider the range of the sine function. So sine, how high and low does sine go? Remember, sine oscillates up and down, right? Goes as high as 1, as low as -1. So this statement right here can be made, is that sine has to be between -1 and 1. We can conclude that then sine of 1 over x has to stay between -1 and 1. Multiply through by x squared to use the squeeze theorem. Okay, so what we're looking at here, when they say multiply through by x squared, we're going to take each piece of this and multiply by x squared. The left, the middle, the right. So when I do that, negative x squared less than or equal to x squared times sine of 1 over x less than or equal to 1. Not 1. I'm multiplying through by x squared. 1 times x squared is x squared. Now, what we're trying to figure out is the squeeze theorem. We're trying to figure out that middle. If you know, so remember the idea of the squeeze theorem. If the upper and the lower meet at some point, and you have proof that what you're trying to find is in between the upper and the lower, it has to meet at the same point. Okay, so it's the idea of this picture up here. The upper and the lower meet at 0, and you know that this other graph is in between them. It has to meet at 0. So if you know the limit on the left and the limit on the right, we can make this happen. So we're trying to do the limit as x approaches 0. So the limit as x approaches 0 of negative x squared, and I want to do the limit as x approaches 0 of x squared. What's the limit as x approaches 0 of x squared?
Mhm.
Yeah, you guys are all busy copying down. Fair enough, fair enough.
Well,
I mean, you can just plug in. You can also think about the graph.
0.
0, yes?
Yeah.
X squared is a parabola. As you approach 0, you're approaching the vertex of 0, 0, yes? Negative x squared is just the same parabola flipped. So both of these equal 0. Okay? Well, based on the fact that those two limits both equal 0, then we know this piece in between them also equals 0. And this is what we talked about a little bit in that squeeze theorem. So officially I can say, since the limit as x approaches 0 of negative x squared equals the limit as x approaches 0 of x squared. Okay, and we already stated that those both equal 0. By squeeze theorem, That's officially what it's called, by squeeze theorem, then the limit as x approaches 0 of x squared sine of 1 over x must equal 0. So there's 4 important statements here. We showed that x squared sine of 1 over x is between negative x squared and positive x squared. We found both of those limits to equal 0. We stated since they are equal to each other, then by squeeze theorem, the middle equals 0 as well. Okay? Example 11 is just a similar piece. Okay? So it just uses the basic idea of cosine. What do we know about cosine? Cosine is going to oscillate between 1 and negative 1, yes? And since cosine oscillates between 1 and negative 1, we can argue that cosine of 1 over x squared oscillates between 1 and negative 1. Okay? So, and again, we can say that, and I don't know if you guys wanted to start with cosine of x is between 1 and negative 1.
Or some of this whole thing would basically just end up equaling 1.
No.
Because if you plug in x squared, it would be.
But we're not going to, so we need this middle piece right here to match this right here for squeeze theorem to work. What am I missing? I'm missing the x squared. So we need to multiply through by x squared like we did on the last one. So that then you'll have negative x squared less than or equal to the x squared cosine of 1 over x squared less than or equal to x squared. Now, what can we already say about the ends? We already know the ends are going to be zeros, yes? And so if the ends are zeros, then the middle is 0. Obviously putting that all down in words, but it's very much similar to the last problem, yes? Okay, so it's going to end up that I'm skipping work because I know the bell's going to ring. By squeeze theorem again, we'll be able to say this limit is 0 as well. Okay, and of course it would be the idea that limit of x squared is 0, and the limit of negative x squared is 0. Okay, so 1.5 for tomorrow, please.